Good morning, evening, afternoon, or whatever time it happens to be that you're watching this video. Today is our video for Thursday, and I wanted to wrap up our discussion about some modern physics topics with something that is near and dear to my heart and to what I studied in college, which is nuclear fission. Because most of you guys probably forgot, whenever I was at Texas A&M, I studied nuclear engineering, which is pretty much all about using, at least what I studied, um, harnessing energy from nuclear fission reactions. So it's learning basically how nuclear fission power plants work. And today I wanted to talk to you a little bit about how that works so that you can better understand how the nuclear power plants that we discussed when we were talking about thermodynamics actually work on a physical level to produce energy. So, um, to get us thinking about that, I basically just wanted to first define to you what fission is. So that's basically where we'll start. Whenever we're talking about fission, um, basically what we're saying is that with fission, heavy atoms, talking about very low on the periodic table, atoms like uranium and plutonium are split apart. And this releases a lot of energy. Basically, energy goes into making atoms in the first place. That strong nuclear force is that force that's there that's basically holding these nuclei together. And if you want to break these atoms apart, it actually requires a lot of energy. But for some atoms, in breaking them apart, you can actually release some of the. If you do it in the right way, then you can release energy in the sense that you can basically cause something to happen that releases the energy that's already contained within the atom. These atoms have this energy because of the strong nuclear force, and if you can figure out a way to break them, then you can release the energy that's already contained within them. So energy is still being conserved, it's just that the energy is inherently there in the matter because of the strong nuclear force. So basically, with the fission process, it starts with nuclear energy. So you're gonna have some heavy atom. Maybe it's an atom of uranium-235. That's the isotope of uranium that gets fissioned in our power plants. And so at the beginning, this this atom has nuclear energy. It has energy contained within its nucleus. And that energy can be tapped if you can figure out a way to split this nucleus up. And for a long time, scientists didn't even think that it was possible to split a nucleus. Because if you think about it, if this is a nucleus with protons and neutrons, then it's going to be very much a positively charged thing. And the only particles that they knew of at the beginning, scientists only at the beginning knew about protons and protons and electrons are both charged. So if you want to split this thing, you have to shoot it with something. You basically want to envision this is you're shooting a bullet at this thing. But if the only bullets that you have are charged, if the only bullets I have are positively charged and negatively charged, then whenever I try to shoot these things at the atom, it's not going to work. If I try to shoot something negative at this atom, then the electron cloud around it is going to repel this negative charge. And if I try to shoot something positive at this atom, then these positive charges are going to end up repelling each other. So you can't really make a atom fission by blasting it with protons or with electrons. But there is another particle that scientists ultimately discovered that is able to make these fission reactions occur, and that particle is the neutron. Let me do a different color for the neutron. So, so with our neutron, The neutron has a zero charge. So if you shoot the neutron at this atom, it is actually able to just pass right into it. And if this neutron has the right energy, then what's going to happen when this neutron hits the atom of uranium 235 is that it's actually going to be absorbed into the atom. So there's going to be an absorption event. And for a moment, the 235 signifies the number of protons and neutrons in the nucleus. So for a brief moment in time, this atom is actually uranium 236. It's a uranium atom that's in an excited state. And it's in an excited state because it just got given this neutron. And if all goes if if things happen right, there's basically two things that can happen from here. This atom can de-excite by just giving off some energy, or if this atom if the conditions are right, then this atom will actually fission. It will actually break into, and that's the interesting thing for us to talk about. So when this thing actually fissions, when it actually splits in two, you get a lot of different things going on, because in the fissioning of this uranium atom, you basically get two chunks of that original nucleus. The original nucleus basically breaks off into two pieces, and these two pieces are called fission products. So these these two pieces are our fission products. And these fission products, when the fission event occurs, these products are moving very, very fast. They're moving like at a fraction of the speed of light. So these fission products are going off in different directions. Maybe one of them goes off in this direction, and maybe the other one goes off in that direction. So these fission products get sent off with a very large amount of velocity. And because they have a lot of velocity, that means that these fission products have kinetic energy, right? We have mass that's moving, so it has kinetic energy. And so that's the first transformation of energy. You have nuclear energy of the atoms of uranium into kinetic energy of the fission products once the atom has actually fissioned. An important thing to think about with these fission products is that when this uranium atom splits in half, the fission products aren't always split evenly, like half of 236 goes here and the other half goes here. Sometimes, or every time basically, there's a certain probability of different kinds of fission products forming, but essentially any nuclei can come out of this fission event. Anything on the periodic table could get born out of this fission product process. So if you're looking at like inside of a nuclear reactor and you're looking at the spent nuclear fuel, these fission products are going to be producing everything on the periodic table, including like gold and silver and platinum and kind of interesting elements that you wouldn't expect to be in a nuclear reactor are there because these fission products that are getting formed from these events are basically anything, can be anything on the periodic table. And these are one of the main byproducts of our fission reaction, and they're where most of the energy where most of the energy ends up. Most of the energy of this reaction ends up in these fission products. But that's not the only thing that ends up getting formed. We also end up producing some gamma rays. So there'll be these high energy gamma rays that end up getting formed from our fission reaction. Those will also get sent out in different directions. But the real important thing and kind of the holy grail of nuclear fission is that the other thing that gets produced in these fission reactions is actually more neutrons. So not only do we get these fission products, and not only do we get these high energy photons, but we actually get more neutrons coming out of this fission reaction. So we're producing, as fission events occur, we're actually producing more neutrons. So, before I talk about what happens with these neutrons, I just wanted to make sure that we followed up what happens with these fission products. Because if you go into, or I guess really what you need to know about these fission reactions is that they are all happening within nuclear fuel, which are like these very small pellets. So if you imagine like a solid cylinder, this is a solid cylinder, the pellets, the nuclear fuel is basically in these solid pellet forms. So all of these fission events are occurring within this solid. And as these fission events are occurring inside of the solid, those fission products are forming and then they're separating and coming off in these different directions, but they're always contained within the solid. So, in other words, when these fission products get formed, it's not like this is happening in empty space and these fission products are flying outward. They're contained within this solid. They travel a very short distance before all of their kinetic energy is basically dissipated into the material. These things basically crash into the things around them as the fission reaction occurs. And you can imagine that if you have all this kinetic energy that basically gets stopped within the material, what do you think is going to happen to this pellet of uranium as these fission events are happening again and again and again? And remember, this I'm just showing what's happening for one atom of uranium 235. There might be millions of atoms of uranium 235 that are doing this very thing every second in this pellet. So you can probably imagine what's happening with this pellet as this kinetic energy gets dissipated is that this thing starts to heat up. That's that's what I'm supposed to be drawing here is that this thing is going to start to heat up. That basically the temperature is going to increase because this kinetic energy is effectively going to get converted into thermal energy. So temperature goes up because that kinetic energy of our fission products gets converted into thermal energy as those fission products start bouncing around and colliding with their surroundings. So that's kind of the energy pathway within the actual nuclear fuel. It goes from nuclear energy to kinetic energy to thermal energy. And the reason that we can actually produce power from nuclear reactions, from fission reactions, is because more neutrons are produced per fission event than go into the reaction, right? We only needed one neutron and one atom of uranium 235 to start this process, and then after the process happened, we got more neutrons out. Um, on average, you get about 2.5 neutrons per fission. So what that means is that you can actually have a chain reaction. One fission event can produce on average two neutrons, so two or three. These three neutrons can then collide with three more atoms of 235. These uranium, this would be uranium 235, uranium 235, uranium 235. These these uranium atoms can fission, and in that fission event, you would produce three more neutrons, and that would happen for each one of these atoms of uranium 235. These neutrons could then collide with nine more atoms of uranium 235. So I could have more uranium 235 here, and here, and here, and then these neutrons could go into these uranium atoms and then cause more fissions, and then you get the idea. This is the idea behind a chain reaction, that basically if you let this go on uncontrolled, then what you have here is exponential growth. One fission event causes three fission events, causes nine fission events, causes the next number of fission events until you have this out of control chain reaction. So that's basically, if you leave this uncontrolled, if this is left uncontrolled, a chain reaction can occur. And in these chain reactions, the number of fission events increases exponentially. And that is basically that's the idea behind nuclear weapons. With a nuclear weapon, you're basically engineering a device to have this chain reaction occur in a way that's uncontrolled. It's an uncontrolled chain reaction in which the number of fission events just increases exponentially. And so that's basically number of fission events increases exponentially. That's the underlying principle behind nuclear weapons. And if you look at the videos of the like atomic bombings of Hiroshima and Nagasaki, and you see those giant mushroom clouds, and you see the videos of like the buildings getting completely demolished from the blast, that's because of all of the energy that's released when you have this process happening on an exponential scale. So you can release an incredible amount of energy like this because of the fact that you have this exponential growth of your reactions where yeah, it's just going to keep growing and growing and growing until all of your fuel gets used up. And that can happen very, very quickly once you get these reactions to start going. That's basically the idea behind nuclear weapons. And the thing that I wanted to talk about next is kind of what makes that different from what we do in nuclear reactors. So, this same kind of thing is happening in a nuclear reactor. The only difference between what happens with like a nuclear weapon and a nuclear reactor is that inside of a nuclear reactor, we change the fuel a little bit and we change the surroundings of the fuel a little bit to add some absorbing material. And so what I'm drawing here are little pieces of absorbing material that are inside of our fuel. And we put these pieces of absorbing material inside of our fuel for a really important reason, and that's because we don't want this reaction to keep going unchecked. We want to be able to control our reaction. So, if for every atom of uranium 235 we're producing 3 neutrons, we want 2 of those neutrons to get absorbed. So, these blue boxes, these would be absorbing material. These are neutron absorbers. Different materials have a tendency to absorb neutrons. Um, Things like a common one is boron, but also we use silver, we use indium, and we use others. So these neutron absorbers are put inside of our reactor so that we can control the number of fission events that occur. As you can see, by adding in these absorbing materials, I started with 3 fission events and I ended up with 3 fission events. And that's really kind of what you would want to happen. You would want for every certain number of fission events to have the same number of fission events the next time, and the same number of fission events the next time, and the same number the next time, so that you're producing a constant amount of power instead of having the amount of power that you're producing increasing exponentially over time. You want it to be happening in a very controlled way. And the way that we in nuclear physics talk about the um, the way that the neutron population is changing in our reactor is with this thing called the multiplication factor. So we need to basically look at the neutrons at 2 different points. Um, we need to look at the neutrons basically here at the first generation, and then we need to look at the neutrons at the next generation. every fission, every generation, we're going to have new neutrons born, right? These neutrons were born out of this generation, and then after these fission events occur, we're going to have more neutrons being born in the second generation. So the the term that's used in nuclear physics to talk about the changing population of these neutrons is this thing called the multiplication factor. So the multiplication factor, for the multiplication factor, they use a symbol K, and the multiplication factor is just a ratio of these neutron populations. So to find the multiplication factor, you basically just divide the number of neutrons that are born in a and then so basically you take the number of neutrons born in, we'll call it, the next generation. So the multiplication factor is the number of neutrons born in the next generation divided by the number of neutrons born in the previous generation. So k is always going to be a number, and it can either be greater than 1, it can be less than 1, or it can be equal to 1. And whether it's greater than 1, less than 1, or equal to 1 can tell you about what's happening to the state of your chain reaction. So basically, what you can imagine is that if you're always producing more neutrons, then you're constantly producing more power, in which case you kind of have this chain reaction situation going. That's what we would call k greater than 1, because the number of neutrons being born in the next generation would always be greater than the number of neutrons born in the previous generation. So the first possibility that we'll talk about for the multiplication factor is when k is greater than 1. If k is greater than 1, we say that the reactor is supercritical. And if the reactor is supercritical, then the number of reactions increases exponentially. So the number of reactions increases exponentially. That's what happens if you're producing more neutrons every time. For every fission event, you're producing more neutrons, then that means your multiplication factor is greater than 1, and that's what we call a supercritical reactor. If a reactor is supercritical, then it's constantly producing more and more neutrons, which means that the number of fission reactions is increasing exponentially, and that means that your power is increasing exponentially. And if your reactor is doing this for too long, then you made a mistake and you basically accidentally made a nuclear weapon. For nuclear reactors to start up, they have to be supercritical, at least for a certain period of time, but you have to do this in a very careful, controlled way in a nuclear reactor. Otherwise, you can start causing big problems. The way that we like our reactors to operate is with a state where k is equal to 1. And that was the state that I was kind of trying to illustrate here, where the number of neutrons in this generation would have been equal to the number produced in the next generation. If you have, if only these three fission, if only these three neutrons cause fission events, then we can get 3 more neutrons in the next generation, and then we can get 3 more neutrons in the next generation, and then we're basically keeping everything in a steady state so that we're not increasing the number of fission events or decreasing the number. We're just keeping it at a steady, constant rate. And that kind of reactor is called a critical reactor. We like our reactors to be critical, and whenever our reactors are operating and producing power, This is the state that they're in, where the number of reactions is constant. That means that the number of reactions isn't changing from minute to minute, and that's what allows nuclear power plants to produce constant power and not have drastic swings where they're producing a lot and then producing a little, and then the amount of power that they're producing is going up and the amount of power that they're producing is going down. They can kind of keep everything nice and steady, and they can produce power 24 hours a day, almost 365 days a year. And then the other possibility is that you're losing neutrons over time, that the number of neutrons born in the previous generation is always greater than the number of that are born in the next one. So your population is decreasing, the population of your neutrons is decreasing over time. And if the population is decreasing, that's what we would call a subcritical reactor. If the reactor is subcritical, then basically what that means is that the number of reactions is going to be decreasing exponentially. So those are basically the three different possibilities that you can have for a reactor depending on what's happening with the neutron population. And because the fission reactions are all based on neutrons, by knowing how your neutrons are changing from uh, from one state to the next, you can get an idea about what's happening with your reactor. If you're producing more neutrons over time, then you're going to have more fission events because with more neutrons, you can cause more fissions. That means that your reactor is supercritical and those reactions are going to increase over time. Um, if you have a constant rate of neutron production, then the amount of neutrons that go in the next generation is the same generation after generation after generation, and that means that the number of reactions that occur doesn't change either. And then if you are losing neutrons, if you are if the next generation has less neutrons than the previous one, then that means that the amount of neutrons in your reactor is decreasing. That means that you have less opportunities for fission events to occur because the fissions are based on neutrons being there, and that means that the number of reactions would decrease exponentially. So those are the different kinds of things that are going on in our nuclear reactor, and those are the different kinds of ways that we can classify what's happening to our reactor in terms of uh, based on the neutron population and based on what's happening with the fission reactions as a result of that changing neutron population. Um, that's all that I have for you guys today, and that's all that I'll have for you for the rest of the week because the next video will be a choice video where you get to basically choose one of 4 videos and answer and write about what you've learned from that. So if you had any questions about the videos from me for this week, feel free to reach out. I'll have my office hours as normal this week. So that would be a good time to get those questions answered. If you can't, uh, you could also send an email, and that would be another good way to reach out. Thanks for your time. Hope you guys are doing well, and I will talk to y'all soon. Take care.